Good day, everyone. Welcome to our first mechanical engineering segment for Introduction to Biomechanical Engineering, wherein we'll be talking about first biomechanics and kinematics. This will be rather short because our objectives for today is not to cover what we've already covered in your previous subjects, but rather to recontextualize what you've learned into the context of human and animal motions and coordinate systems. So these will be our um, coverage for today. We will talk about briefly about the human control systems, then go through basic human motions, the joints, and conventions for the joint angles. Now, humans, they're kind of like machines, not very similar to machines, but they can be contextualized as machines. So what you see here is a diagram for forward kinematics, which perhaps we will cover at some point. But if you look at the control system or the control diagram, you start with neural commands from your brain, and then it travels to your muscles, which through geometry of your body translates them into motion. And of course, as you move, you pick up sensory feedback from your um, sense of sense of sight, sense of hearing, sense of touch, sense of location or proprioception, and you adjust accordingly. So in some ways, we are like machines. And because of that, we can transfer a little bit of what we know in mechanical engineering, particularly machine design, into the human or the animal body context. But it needs a little bit of help. The reason why is that medicine and engineering, they were separate for a while, so they developed their own respective conventions. And when the time came to finally um, develop an interdisciplinary approach for biomechanics, there were conventions that you couldn't just, get rid of. It's fine. It's a little bit confusing at first, but they're all basically referring to the same thing. Just uh, think of it as using a different languages, essentially. So this is nothing new to us at this point. These are the anatomical planes for the human body on the left, and for animals, at least um, quadruped animals on the right. Now, we have the sagittal plane, which splits our body up into left side and right side. We have our frontal plane, which separates our front and back, or the anterior and posterior. And we have the transverse plane, which separates our superior and inferior parts of the body. So these labels are actually general labels for the planes. The sagittal plane that splits the body exactly at the halfway point is called the mid-sagittal plane. But any plane that is parallel to the mid-sagittal plane can be called the sagittal plane. Likewise, for the transverse plane, you can call any plane that is parallel to this midway transverse plane as a transverse plane. Now, with respect to that, we also have axes associated with each plane. Now, the labeling of these axes are kind of weird, except for the vertical axis. So the vertical axis can also be called as the longitudinal axis. It's the axis from that um, points to up and down. So for the sagittal plane, it is associated with the frontal axis, which is kind of weird for us because frontal axis, but it's not pointing front and back. And for the frontal plane, we have the sagittal axis, which points forward and backward instead of left or right. So this is where we come into the conventions with regards to anatomy and medicine, because the planes, the anatomical planes, take precedence over the axis. So this is kind of different from our mathematical and engineering approach, where we are used to defining planes through their normal vectors or normal axes, but that's fine. Just take a little bit to soak it in, just so that you don't get confused. Another illustration here for the human anatomical system shows you the direction of naming conventions. So these have been covered by our veterinary medicine counterparts. So for the frontal plane, the front and back are referred to as the anterior and posterior, respectively. For the sagittal plane, the side to side. If you're farther out, you call this as lateral. While if you're approaching the mid plane, the mid sagittal plane, you refer to things as medial. Now, for the transverse plane, since we're humans, we use the term superior and inferior, which is just top and bottom, although there's an English context underneath that. Now, for the limbs, we have the distal and the proximal. The proximal is closer to the core of the body, while the distal is farther out. Now, for animals, especially ones that walk on all fours or all manner of legs, um, instead of using the superior and inferior directions, they have the cranial and the caudal directions. And they also have the dorsal and the ventral directions. But yeah, I didn't include this in the anatomical plane discussion. Oh, there they are. Yeah, it's there in the animal slide. All right. Now for human motions, because the conventions are putting precedence on the planes, the definitions of certain human motions are actually linked to them. So if you see here in our human motions table, we have a column for the axis, which is, well, what we're used to, and the plane, which is where the motion is usually defined. So first and foremost, the flexion and extension motions, they typically occur at the frontal axis or the side-to-side axis. And that side-to-side axis, it lies, that motion, that flexing and extending, it lies on the sagittal plane, which is the midplane. It's kind of confusing, but it kind of works. So flexion is the inward motion and extension is the outward motion. Now, if you look at the mirror, looking at your anterior side, um, when you extend your arm outward, that's called abduction. When you pull your arms inward, that's adduction. So this at the sagittal axis, which is the front back axis, and it is and the motion is essentially being performed on the frontal plane. Now for the longitudinal axis or the transverse axis or the vertical axis, I mean, um, we limit the term rotation for any angular motion that is along the vertical or the longitudinal axis. So when we say rotation, it's typically referring to vertical pivots or vertically oriented rotation. So like for example, your neck, when you rotate it from clockwise to counterclockwise, that is termed as rotation. If you can rotate your leg inward, that's called the medial rotation because it's approaching the midplane. And if you rotate your leg outwards, that is lateral rotation. Now, these are terms for the flexing or the moving of a specific joint. So usually it's only one joint or two that's involved. If there are multiple joints that are not really linked together, this is what we call circumduction. So circumduction is kind of like rotation, but you are involving more than one joint, and those joints are not in the same place all at once. So like for example, if you rotate your hand, that is a circumduction. So in a circumduction, there are multiple things happening. There can be flexion of a muscle, an extension, or there can also be an abduction or an adduction of specific muscles. So circumduction is a more complex kind of mechanical rotation. Now, these are not the only terms for human motion. There are others, specifically for regions of our body. So, like for example, for our forearms, we have two additional terms for the circumduction. So, if you rotate your hands such that your palm faces quote unquote downward, that is called pronation. If you rotate your hand so that your palm faces upward, that is supination. Now, for your foot, if you raise your toes, that is called dorsiflexion. And if you point your toes down, that is plantar flexion. So next, if you try to rotate your foot, although I don't think you can force this, or if you can actually do it by will, you are a anatomical master race. So yeah, if you try to rotate your foot inward, it's called inversion. The outward motion is eversion. While for your thumb and fingers, if you bring them together, that is called opposition. So that's where the opposable thumbs met, concept comes from, opposable thumbs. And if you bring them out again, so like they're no longer touching, that's called reposition. So these motions are for specific parts of the body, and there are many other terms, especially for the jaw, but we will not cover that for uh, this lecture. However, um, these are not like flexion and extension because during these motion terms in specific parts of the body, there are multiple muscles that are being engaged. So they're much better. You can think of them as kind of um, specific circumductions of different muscles instead of just flexing and extending. So yes, so those are human motions. Now for the joints, this is where the fun begins, because there are multiple types of joints in the human body, and some of them don't have precise analogies to, or rather, they don't have precise analogs to mechanical systems. Now, we can classify joints by either their makeup, by that I mean their component structure, what they're made of, and we can also separate them by the degree of freedom that they exhibit. So first, human joints by makeup, we have the fibrous joint. These are joints that are uh, connected by connective tissue, the tissue that connects different parts of our body. The unique thing about this fibrous joint is that there's very little space in between them. So, like for example, the suture joints in your skull, they are fibrous joints. There's not a lot of space between them, so that means their movement is completely or almost completely restricted. The second type is the cartilaginous joint. Uh, this has a little more freedom because there is cartilage in the gap between the bones, but they are also a little more restrictive. Not as restrictive as the fibrous joint because there's almost nothing between the bones, but there's still not a lot of wiggle room in the cartilaginous joint. Now, the third type that we most associate with joints is the synovial joint. So, these are joints that are characterized by having a joint capsule, which protects the mating bones from wearing and allows for motion of that joint. Now, for the motion classification of joints, uh, there is a there's a connection between the makeup and the motion that each joint exhibits. So, for example, joints that are synarthrosis, These are wholly immobile, so essentially they are fibrous joints. Analogies for them in mechanical engineering will be the weld joints or the bolt connections. Basically, these are the joints that are not joints. They don't allow movement between mating geometries. They're just meant to be assembled and fixed together. Next is the amphiarthrosis, which allows some movement but not a lot. So an example of this is aside from the cartilage that is connecting um, parts of your pelvic bone system, is the connection between vertebrae in your spine. So they are actually flexible. There's quite a lot of space between them, but they don't allow a whole lot of movement. So if this joint was a synarthrosis, you wouldn't be able to move your spine at all. However, they're not as flexible. I am not sure if this is the right analogy also for mechanical engineering systems. So they could be similar to vibration of isolators, wherein they kind of allow some motion, but they are not supposed to permit a whole lot of motion, if you want to think of it that way. The next one is called diarthrosis, which, because of their definition, can only be done by synovial joints. So these are the joints that are actually kinematic joints, essentially. So they're analogous to kinematic pairs. And we will explore the diarthrosis joints or the synovial joints by their motion type. So if you look at your skeletal system, there are at least six types of joints, six types of synovial joints, I mean, in your body. And some of them are very plentiful, but some of them are very rare and only show up in specific parts of your body. So the first one that shows up is what we call the hinge joint. So the hinge joint, hold on. Okay, sorry about that. So yeah, the hinge joint, these are joints that allow flexion and extension motions. Could also be abduction and adduction, but only one of those motions. So an example of this would be the humeroradial joint in your elbow. So your elbow allows flexion and extension. So the degree of freedom of the system is 1. That's 1 DOF. And it is most analogous to a revolute joint. So yeah, examples of these are your elbow joint, the joints between your phalanges, and um, although I've seen literature that says the knee joint is not precisely a hinge joint, but it kind of functions as a hinge joint. I'll have to confirm that. Now, among the joints in your body, the hinge joint is not the only one that acts like an R joint. We also have what we call the pivot joint. So the difference between these two is that for the hinge joint, it allows a change in angle between the connecting bones. So it allows flexible flexion and extension. However, the pivot joint, it only allows longitudinal rotation or anatomical rotation. So the bones, they are not changing their angle with respect to each other, but rather one of them is being twisted or not twisted, I mean rotating in their quote unquote, they're rotating with respect to the other bone. So they're kind of like our joints, but the pieces are kind of in the same axis, you can think of it, or rather they are in parallel axis. One example of this would be the atlantoaxial joint. This is the one that allows the clockwise, counterclockwise motion of your skull with respect to your neck. So your skull does not change its orientation with respect to your neck if you're pivoting about the atlantoaxial joint. Another one is the both the proximal and the distal radioulnar joint. These are the two joints that allow the pronation and supination of your hand. You can see it here pictured. So your radius is essentially coupled to the ulna in a socket. So that kind of connection allows for the ulna to, or rather the radius to rotate and allow your hand to pronate or supinate in kind. So yeah, those are the two R joint like joints in your body. Next, we have what we call the ball and socket joint. So this is kind of like, this is the analogy to the spherical joint, and of course, as you know, ball and socket joints, they allow rotation in three axes. So these allow for both flexion, extension, abduction, adduction, and anatomical rotation. So there are, I believe, um, two specific instances of these, the shoulder joint and the hip joint. So these are the only two types of ball and socket joints that we have. Some animals, they have additional ball and socket joints elsewhere, but you can look that up if you have the time. So aside from the ball and socket joint, we have what we call the condyloid joint. So if you look at the ball and socket joint, it's like essentially a socket, a ball on the end of one bone connecting to a spherical socket. So there's a spherical end of one bone connecting to a spherical depression or spherical socket. For the condyloid joint, think of that socket being ellipsoid instead of spherical. So the socket, the ball end of the bone is instead of spherical, it's ellipsoid, and it fits into an ellipsoid socket. So what happens is that one of the motions, one of the three action rotations that you originally had disappears. Like you can't do that anymore. So condyloid joints, they are ellipsoid joints. They allow flexion and extension and abduction and adduction. So their degree of freedom is only two. And although we have the universal joint, which has two rotational degrees of freedom, I'm not sure if this is analogous because um, it's basically made up of two R joints, and this thing is just one joint. The condylar joint is just one joint essentially. So examples of these are your wrists, your knuckles, and the atlanto-occipital joint, which connects your skull to your neck. So in the previous example, we also have another head to neck joint, that is the atlantoaxial joint. Apologies if I mistakenly mentioned it, but the atlantoaxial joint is between the first vertebra of your neck and the second vertebra of your neck. So that one allows longitudinal rotation, while the atlanto-occipital skull, it is a condyloid joint that allows your head to bend down, bend up, and bend to the left, bend to the right. Now for your wrist, although you may think na, oh, I can turn my hands outward and inward, that motion is actually from the radioulnar joints. They are not in the wrist. You can try this. Try to restrict your the part of your forearm just before the wrist, and try to pronate and supinate it. It's really hard. Like maybe if you're anatomically strange, you can do it. But if you restrict the radioulnar part of your arm, or rather the distal part of your arm, you can't really do pronation or supination. Like it's really hard. You're limited to flexion, extension, bending your hand side to side. So that's abduction and adduction. So yeah, your knuckle joints, the bases of your fingers are also the same. So you can bend your fingers down, up. You can also bend them side to side, like cute little creatures. So you can also twist them, like you can make them to rotate like a cone and form kind of an image of a cone. That is still 2 degrees of freedom. It's not rotation longitudinal rotation along the joint. So yeah, that's the difference. Next, we have the saddle joint, wherein you can kind of think of it as two piatos kind of sitting next to each other. So there's this one part of the connect. There's one connecting bone that has an end that kind of looks like a Pringles. So sorry, not piatos, it's Pringles, and the other end is kind of like also Pringles. And if you connect them together, they can sort of bend. They can bend in one axis, two axis, and they can kind of pivot, but not a whole lot. So it's kind of like a limited spherical joint. The only limitation is the longitudinal rotation. Examples of this is a joint found in your heel, but more famously, it's in also in your thumb joint. So your thumb joint at the base has a saddle joint. You can flex, extend your thumb. You can abduct, adduct your thumb, but there is some wiggle room for rotation, but it's really hard to activate. You have to kind of make your thumb do the longitudinal rotation using your other hand, but yeah, it's essentially a saddle joint. The last part is the hardest to imagine. This is the plane joint. So it's essentially the planar joint in kinematics. So it has 3 degrees of freedom. The joints can translate along the plane to a limited degree. They can also rotate with respect to each other. There are several joints of this in your body, but they are not um they're not as obvious. So one of these is the acromioclavicular joint, which connects your clavicle to your, I think, the shoulder scapula. Yeah. So this joint kind of allows some wiggle room to displace, but not a whole lot. They can also rotate, but not a whole lot. More examples would be the joints between your carpal bones. If you want to imagine what your carpal bones look like, they're kind of like bones smushed together. They're like little knobs. Between those knobs, they can kind of slide around and kind of rotate a little bit with respect to each other. It kind of happens as you move your hand around. This also happens for your foot. So the equivalent of your carpal bones in your foot is are the tarsal bones. So they're also kind of smushed together. They can slide a bit around, but not a whole lot. The joints between your vertebra also do this. So yeah, um, because they only allow limited range of motion. Of course, if the vertebra accidentally goes too far, it translates too far, you could get a hernia or a displaced disc, which is really bad. So actually, all of these 6 types of synovial joints are found in your hand, strangely. So if you want to examine those, or at least if you want to remember all those 6 types, you can just recall which types of joints go to which part of your hand. So, yes. Huh. All right. So there is this funny phenomenon of animals, or at least a specific genus of plant hopper that has gears between their hip joints. So, um, the genus Esus, this it's a plant hopper. This was introduced to me by our machine elements professor before, but these insects, when they jump, they want to make sure that they don't twist in the air. So to do that, their legs have to be synchronized so that when they jump, they just jump stably. They don't just twist around like fleas. So the plant hopper, this genus specifically, they got around that by putting teeth between the bases of their legs so that when they jump, their legs are always in sync. So yeah, it's pretty cool. Um, so far, this is the only animal that has gear teeth anywhere in their body. Like the maybe there will be in the future, but I'm not really sure. So yeah, it's kind of unique. Next, we have joint angles. This is gonna be quick. For angle types or joint angles, they can be separated into relative measurements and absolute measurements. So when you measure angles relatively, you're measuring the angle between the bones themselves. So, like, take for example, the knee angle. So, typically, when you say knee angle, it's the angle between your femur and your shin. Now, there are other types of angles that are defined instead of being relative to the bones, they are defined relative to a reference line. So, for example, the thigh angle, it can be the angle measured um, of your femur versus the horizontal plane. So, it can be the plane can be resting on your knee, it can be resting on your hip. Um, some some research papers actually use the vertical plane, so it really depends on um, which reference plane you're referring to. Whenever you do so, it's better to just define it in your research instead of assuming. Uh, so yeah. So thigh angle. You also have the shank angle. Um, yes. Your shin is also your shank. I think shank is more common for um animals. Common term for animals. So yeah. And you can see here these angles, they kind of have like little attachment names, a little extra on the side. So for example, the knee angle example here, it has right sagittal knee angle. So the right comes from the fact that it's the right leg, of course, but it says sagittal. So sagittal refers to the plane wherein the angle is lying flat against. So this is where again in anatomical conventions, the anatomical plane takes precedence in the naming of angles. And that's pretty much it. Oh, I didn't remove the orientation slide. So yes, um, that is it for kinematics. Here are my references. I hope you are safe as you are viewing this, and I hope that you have a great day ahead. Thank you so much.